Hello everyone, welcome you back for the sessions on the miniaturization and as well as the MEMS fabrication methods. As the name suggests that miniaturization means the very huge components, or it may be a larger size components, or it may be the devices, it should be reduced to a smaller one, that too especially which is ranging from a 1 mm to a 1 centimeter. As you know that the smaller the dimension gives rise to a many optional advantages and also some of the disadvantages also, depending upon the type of the application. Thus, the operational advantages are such as the soft springs, high resonance frequency, or greater sensitivity, or it may be low thermal masses. For example, if you take an example with respect to the heat transfer, if the component or if the device is of too big means, then the heat transfer material what it is required is also too big. But here in this case, as we know that in the case of the MEMS technology, the components or it may be the devices is of very small, the heat transfer or the heat removal rate from the devices or it may be the components is also a easier task. Smaller the size of the MEMS, the devices with a less intrusive in the biological application, that too especially either it may be insertion in the case of the nerves, or it may be directly insertion in the human body itself. Being a small also means that MEMS devices can integrate it intrusively in a crucial system such as a portable electronic devices, or it may be a medical instruments, or even it may be a implants. The best example is with respect to the capsule endoscope. As you know that the capsule size, it will be somewhere around a 1 inch, and as well as a diameter somewhere around not more than 8 to 10 mm. 8 to 10 mm is too large. If it will be somewhere more, it will be around 6 mm only. These type of endoscopes, it has to be fabricated that if it swallows, it has to move in the what we can say in the digestive system, or it may be in the tract very easily. From the practical point of view, the smaller devices footprints leads to a more devices per wafer and also the greater economy scale. Hence, the MEMS devices generally the scales favorably with a miniaturization. The next topic what we are discussing is with respect to the fabrication methods. Now here, as with respect to the fabrication method concern, the MEMS as a size starts decreasing it, even the complexity in some cases is also increasing it. But the another major concern is the utilization of the less as a part and a little scale application in a light and low multifaceted nature. These are all some of the what we can say the general utilization systems, especially in the case of the 3D materials. Now, the MEMS manufacturers requires a high volume of IC styles clusters. Preparing that includes either it may be the expansion or the subtraction, or it may be a two-dimensional layers, or it may be a three-dimensional layers, or it may be photolithography, or it may be a compound scratchings, or it may be a etching. The extra layers can be likewise be included with the help of the etching, so that to hold the procedures, and also the addition through the conciliatory the space layer. Now here the failure of the demonstration demonstrates the potential may cite a qualitatively of the MEMS framework by the expansion of the free basics layer. Now, if you take an example with respect to a 2-layer, or it may be a 3-level, or it may be 4-level, or it may be 5-level. In the case of the 2-level, a simple sensors. Here in this case, over the silicon substrate, a motors, its construction is very easy. But in the case of the 3 levels, along with the motors, the bearings and as well as the gears, it has to be fabricated. This it needs a little complication, and also the technological involvement in this is also increasing it. If you take an example of the 4th level, there what has happened is the advanced actuators with a simple systems. Here in this case, the linkages will also be there, and also the actuation and how the linkages are joined. It is joined by means of the pin joints. Even those joints also it has to be designed. There were still the complication with respect to the MEMS is increased. With respect to the fifth level also, here what has happened, the bearings, the linkages, gears and even the motors or the entire thing is placed on the wafer. This is nothing but a fifth level where the complication with respect to the design of the MEMS is increasing it. As the complication starts increasing it, even the procedures what we are adopting with respect to the fabrication concerns is also increasing it. The next topic what we are discussing is with respect to the photolithography. As the name suggests that there is a two terms are there, which is nothing but a photo and another one is nothing but a lithography. Put together is nothing but a photolithography. The most common lithographic process involves the deposition of a photosensitive chemicals which is also called as a photoresist, or in a simpler way it is also called as the resist on the wafers, and then which is exposed to the light of the mask and removing the photoresist material that has been modified by the light. The starting point of the photolithographic process is to coat a wafer with a photoresist through a spin coating. A wafer is held in a rotating state. The photoresist is applied to the center and the wafer is rest in position. Then because of the speed, because of the what we can say the rotation of the speed, the material or the what we can say the photoresist material is distributed over the entire wafer. After the wafer spinning is stopped, a uniform thin layer photoresist is coated and the front surface of the wafer is processed. The thickness of the photoresist is generally varying from 1 mm to 10 mm. The photolithographic patterning involves a multiple steps. As we know that a wafer is the first covered with a uniform thin layer which is called as the resist, or it's also called as a photoresist. A mask consisting of a transparent layer, which is either it may be a glass or it may be a quartz or even with a opaque features, are brought closer to a photo coated wafer with a high energy collimated light ray striking the mask wafer assembly. Now, the resist region that are not covered by the opaque features are exposed, changing the chemical composition of the resist. The positive resist, the exposed by the light causes the resist to be more soluble and in the wet chemical developer. This allows the opaque features on the mask and faithfully transferred to the wafer. Now here in this case, as we know that the pattern in the photoresist can be further transferred to the underlying layer using the photoresist mask. The wafer is covered by means of a spin covered layer photoresist, which is a photolithographically patterned similar to the method that discussed in the previous one. The wafer is then immersed in a chemical solution that is preferably etched by and the thin film but not the photoresist. As we know that the photoresist is then preferably removed, leaving a thin film behind as a pattern. See, now here the basic steps with respect to the photolithography is explained here. The first one is nothing but a coating with a resist. Now there are two layers will be there. The first one is nothing but a substrate. Over the substrate a resist will be laid. Now after laying the resist, over which a mask will be developed. This mask, it consists of the two things, opaque layer, the another one is nothing but a transparent layer. In the transparent layer, if the light is exposed, where the etching or the material removal in the resist is taken place. Even here also the transfer pattern, it can be done either by means of the etching or by means of a doping or by means of a deposit films. These are all the different methods where it can be transfer of the pattern is taking place. Then after the strip is resisted, then the component it can be used for the application purpose.